9.1 Sequences. In previous courses, we defined a mathematical sequence as an ordered set of elements. For example, 2n minus 1 from n equals 1 to infinity represents the infinite sequence of odd numbers. We define a sequence to be a function whose domain is the set of positive integers. And what that means is that if the domain is the set of positive integers, then, like the first number in this set right here would be domain of 1, and then the number would be 1. So this would be domain number 2, the number would be 3. Domain number 3, term 3 is 5. Term 4 is 7. So these are like ordered pairs, 1, 1, 2, 3, 3, 5, 4, 7. So that's why it's saying your domain is the set of positive integers. It is customary to use subscript notation in order to identify each member in the sequence. So instead of, looking at it as 1, 1, you're going to call that first 1 in the set of numbers a sub 1, the second one a sub 2, the third one a sub 3, and then you'll call your whole set a sub n. And that just indicates that ordinal position, first, second, third, and fourth, so on. The number a sub n is the nth term of the sequence, and the entire sequence is represented in brackets as sequence a sub n. So example number 1, we're going to write the terms of the explicitly defined sequence. So we're basically just going to open up a bracket here, or a brace. This isn't a bracket, it's a brace. And we're going to put the number 1 in for n. And when we do that, we should get 1/2. We're going to put the number 2 in, and we should get 3/3. And I'm going to write it this time as 3/3, but we normally would say 1, okay? But I'm going to show you why in a minute. If we put a 3 in, we should get 5/4. If we put a 4 in, we should get 7/5. Put a 5 in, we get 9/6, which we would reduce to 3/2. But I'm going to leave it like that. I can't remember what number we were on. 1, 2, 3, 4, 5, 6. Put a 6 in, I get 11/7. Put a 7 in, I get 13/8. And I mean, we're doing way more than you need to do here. I just wanted to kind of show you the pattern. The reason I kept it 3/3, we've already got the pattern here, but let's say you were needing to give me the pattern. Like if I gave you this list of numbers and you needed to give that pattern back to me. Do you see how you, in the numerator, you have 1, 3, 5, 7, 9, 11, 13. And one way to talk about all of the odd numbers is to say 2n minus 1 or 2n plus 1. And it depends on what you want to start with, which odd number you want to start with, and it depends on what n you're starting with, okay? But for this one, when they don't specify, then you always assume it's starting at n equals 1. But you'll see later on that some of them start at n equals 0, which is fine. But when they do a summation, they will later on sometimes start at 0. But sequences almost always start at 1, just because of what they are, because they're it's the set of positive integers. Well, that 0 doesn't include the set of positive integers for the domain. So by definition of a sequence, we don't start at 0. But if you wanted me to tell you what how to get in terms of n what this sequence was, and I gave it to you like this. And again, this is what I normally would have you write. But if I gave you that, do you see how it might have been a little bit hard to see? Because you've got 1, and then you've got 1, then you got 5, 7, but then you got a 3. Then you got 11, 13. But if you would have thought about 1 as 3/3 and 3/2 as 9/6, you would have seen the pattern in the numerator. the pattern in the denominator is just going, by ones. So that's just n plus 1. And you knew that it was going to be n plus 1 because it started with 2 and, just continued on increasing by 1 in the denominator. So I think you would have, I just want to show you ways to think about things whenever I'm asking you to tell me what the sequence is. You can change some of your numbers so that you can see a pattern, and it makes it easier to write the sequence. All right, the next one. Again, we're just going to put a 1 in for n, and if we put a 1 in for n, we should get 1 over 1. Okay, I'm going to go ahead and just write 1. If we put a 2 in, we should get 3/4. If we put a 3 in, we should get 7/9. If we put a 4 in, we should get 15/16. Put a 5 in, we should get 31 over 25. And that's your sequence there. Again, that one might have been a little bit difficult to write, but you can kind of see that you're perfect, or not perfect, I was going to say perfect cubes, but I didn't mean that, that you're 2 to the first, 2 to the second, 2 to the third, and then you're subtracting 1. So this is 1 away from 2 squared, 1 away from 2 cubed, 1 away from 2 to the fourth, 1 away from 2 to the fifth. So you should be thinking like in those terms, and of course, down in the bottom, you've got, your 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So again, just start thinking in those terms, because right now we're doing the easy part of just being given a sequence and giving us the numbers. That's the easy part. You can do that, I could have 6th grade do that. We're going to be doing it the opposite of giving the numbers, and we're going to have to figure out what the sequence is. Example number 2. Your first term is -1, and the rule is, or your nth term, I guess you could say, is 2 times a sub n minus 1 plus 3. When you see a sub n minus 1, that's the previous term, okay? So when you're writing your terms, you already knew that this one was -1. So if I want to get my second term, so let's say I want a sub 2. Do you see how I'm going to be putting in a sub 1 here? So to get my second term, I'm going to be using my first term, okay? So that's called recursively defined. That means, I could give you the 100th term if I knew the 99th. Where on this other, the explicitly defined for part A and B, you could give me, if I wanted the 100th term, I just put 100 in for n. But if I wanted the 100th term on a recursively defined sequence, I would have to know the 99th term. So it's just a different type of definition. So if I put, 2 times -1, -2 plus 3, I get +1. Now to find the third term, I'm going to put my second term in. I get 5. Find the fourth term. I'm going to put my third term in. I get 13. Pencils not wanting to write today. If I wanted to find my fifth term, I would have to put my fourth term in. And so I would get 29. And then I'm just going to go ... Okay? Part C. Or actually, that should be a B, shouldn't it? Because it's the... Anyway. So my first term is 5. If I want my second term, I'm going to go times my first. Okay, so I did my, because my k is 1, right? My k is 1. So if I want my second term, this is going to be 2 over 2 times my first term. And so my first term was 5, and then my second term is 5. My third term, my k would be 2. So this would be 3 over 2, and times my previous term. And so that's going to give me 15 halves. I want my fourth term. My k is 3. So this would be 15. Dot, dot, dot. Okay, so some of these are, just a little weird. You have to kind of think about what you're doing and make sure you remember, okay, what term am I on? Sometimes we need to develop the rule for the nth term of a sequence given the first few terms. This usually takes a little creative thought and some pattern recognition. So again, this is like what I was telling you before, that it helps if you're thinking, like, oh, this number could be, this number or this number, especially when it's fractions. But you always have your a sub 1, right? Because you can see it, you've got your list here. And then you're trying to look at what is going on in the sequence, okay? I notice that I am subtracting 4 every single time, okay? This is called an arithmetic sequence. When you have an arithmetic sequence, you're just adding or subtracting the same number. I mean, you could say you're adding a negative number every time, so instead of adding or subtracting, you could say always adding positive or negative number every single time. So what you could think of it as is that your second term is some number d plus your first term, right? And so if my second term was -3, some number d plus my first term, and then you could solve for d. Like if you felt like, oh, well, I don't know. So then your d is -4. So a sub n. And you're like, okay, well, I've got my a sub 1. Then I've got my a sub 1 plus 4. Maybe I should have said -4. I should have said plus -4 or -4. Sorry about that. So a sub 1 minus 4. Come on. Okay. And then instead of making it like a sub 2 minus 4, a sub 3 minus 4, what if we thought about it as being a sub 1 minus 4 times 2, right? Because you're really just subtracting 4, and then a sub 1 minus 4 times 3, comma, okay? Now, this is not your sequence yet. I'm trying to just kind of work your way through it and have you think about it. So if you're thinking about it, how can we write it so that it only includes numbers and n? It's going to look something like up here, like something that we did up here. Like it's going to look like that sequence or that sequence. And look at what's happening. This is my third term, and I've got a 2. My fourth term, I have a 3. My second term, really, there was a 1 here, but I didn't write it, okay? So you can see that is decreasing by 1, and it's 1 increasing by 1, but it's 1 less than what you started with, okay? So I'm going to go over here and just do some scratch work real quick. So it actually is a sub 1 plus negative 4 times n minus 1. Now, for my first n, it's just going to be a sub 1. So for n equals 1, my value is just n equals, or a sub 1. For n equals 2, it would have been a sub 1 minus 4. For n equals 3, it would have been a sub 1 plus negative 4 times 2. So now what we're going to do, since we've got the pattern here, we're going to put our a sub 1 in, and we're going to simplify. So 1 minus 4n plus 4, so this is going to be 5 minus 4n. So our a sub n is 5 minus 4n. Okay? And I might have, taken you the long way around. You might have seen it right away, so I apologize if you did. Sometimes I over-explain things. All right, next one. So your a sub 1 is negative 1. A sub 2, 1/2. Look what's happening in the numerator. It goes negative 1, positive 1, negative 1, positive 1. Okay? In the denominator, it's going 1, 2, 3, 4. Does anyone have any ideas for what we could do for our a sub n here? If you do, hit pause and try and write it. All right. Did anyone have the idea that to get negative 1, positive 1, negative 1, positive 1, that you could have gone negative 1 to the n, and since it was going 1, 2, 3, 4, this is just n. I bet some of you got that one. Okay, part C. This one, the numerator's going 1, square root of 2, square root of 3, 1. Okay, so I'm like, Then it's going 2, 4, 8, 8. Does anyone have the idea to change this one to an equivalent fraction? I did, because I was thinking square root of 1 in the numerator, square root of 2 in the numerator, square root of 3 in the numerator, square root of 4 in the numerator. And then I was thinking 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. And then I was thinking, does the square root of 4 over 16, which would be 2 over 16, does it reduce to 1/8? Yes, it does. Bingo. So you can see that your numerator is doing square root of 1, square root of 2, square root of 3, square root of 4, which is going to be square root of n. Over, and then this is going 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the n. This one I think was kind of hard to figure out, but think about what function goes from 0 to 1 to negative 1. Is there a function that kind of, if you were just looking at specific things, goes 1, 0, negative 1, 0, 1, 0, negative 1? Any function that you can think of. How about sine or cosine? So I chose sine. And let's see if this works. If I put 1 in, I've got the sine of pi over 2, which is 1. If I put a 2 in, I've got the sine of pi, which is 0. If I put a 3 in, I've got the sine of 3 pi over 2, -1. Okay, there are other answers for this, but that's the one I chose. You could have done it with cosine also. You just would have had a different argument. All right, so now for AP Calculus, we will be looking at sequences that are said to converge. That is, the terms of the sequence approach a limiting value. So consider the sequence 1 over 2 to the n as n becomes infinitely large. The sequence approaches 0. However, a sequence that oscillates between values or grows infinitely large is said to diverge. So consider the behavior of the sequence ln k. The sequence is divergent because the limit as k goes to infinity of ln k is infinity. So formally we say that if the sequence a sub n is a sequence such that f of n equals a sub n for every positive integer n, then the limit as n goes to infinity of a sub n is L. So you're looking at it as a function, right? And you're looking at, does it approach some value? If it does, then it converges. If it goes to infinity or negative infinity, or if it just jumps from 2 to -2, 2 to -2, or, it might jump +1, -1, then +2, -2, then +3, -3. If it does anything like that, and it doesn't basically go to one number, then it diverges, okay? It only converges when it goes to one number as your n's go to infinity. All right, so now find the limit of the sequence whose nth term is given. So we're just going to say the limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of 1 plus 1 over n to the n. Does that look familiar? Is anyone thinking of this function? I bet a few of you are thinking that function, because we know that the limit of this function, if we took the limit of that function that I just defined as x goes to infinity, I'm going to just put f of x here so I don't have to write the whole thing again, is e. So therefore, this is approaching e also, okay? So the limit of that sequence is e. So as you put your values in, 1, 2, 3, as you're going to infinity, they're going to get closer and closer and closer to 2.71, okay, to that e value. Part B, a sub n is the cosine of 1 over n. So we've got the limit as n goes to infinity of a sub n is equal to the limit as n goes to infinity of cosine 1 over n. And when I put infinity in here, this is approaching cosine 0. And cosine 0 is approaching 1. So my answer to my limit is 1. So if these were, if someone asked you, does this sequence converge? Since this limit of the nth term equals one finite number, then you would say that those sequences converge because they equal a finite value. The limit of the nth term, okay? So converging and diverging sequences. Determine whether the sequence converges or diverges. So I'm going to look at just like if I put a 1 in, if I put a 2 in, what happens? So 5 plus -1 to the 1, is going to give me 4. And then 5 plus -1 to the 2 is going to give me 6. 5 plus negative 1 to the 3 is going to give me 4. 5 plus negative 1 to the 4 is going to give me 6. So do you see how it just keeps jumping? Like the terms are all alternating. 4, 6, 4, 6. And if the terms alternate, then the limit as n goes to infinity of b sub n oscillates. And therefore, sequence diverges. Okay, so our answer to that would be diverges, because it goes, 4, 6, 4, 6. It just keeps alternating like that. Okay, so the next one, if I put a 1 in, I get 2 over negative 2, so I basically get negative 1. If I put a 2 in, I get 4 over negative 5. If I put a 3 in, I get 6 over negative 8. If I put a 4 in, I get 8 over negative 11, ... So it's kind of hard to see what this is doing, all right? I mean, you kind of can, but let's look at the limit as n goes to infinity of that nth term. So, excuse me. You could get infinity divided by infinity and use L'Hopital's, right? Or we also talked about, the highest term in the numerator divided by the highest term in the denominator, looking at it as 2n over negative 3n, because those are your strongest terms. Either way, this is going to give you a value of negative 2/3, so therefore your sequence converges. All right, so use L'Hopital's rule to determine whether the sequence converges or diverges. So we are going to, it is kind of a good idea to always just like imagine what your sequence would look like, by putting in your values. They specifically told us to use L'Hopital's rule, so you're assuming you're going to be using a limit. So technically you would probably go straight to that, but I think it's a good idea just for later on when we're doing other things to always look at your sequence, especially if if you see it on the AP exam or something, they might give you a summation sequence. And I think it's a very good idea just to see what you have, because sometimes that will help you. So if I put a 1 in, for this one, ooh, look what happens when I put a 1 in. This is a bad sequence. This gives me division by 0 when I put a 1 in. Yeah, that's a bad thing. I didn't do that on my paper. Let's go ahead and just solve this for that, but I don't like that sequence because of that. Unless they would have stated n equals 2. Maybe they would have stated that they wouldn't have started at 1, that n equals 2 or something like that. But anyway, so on this one, if you're doing your limit, you've got infinity divided by infinity. And so if I take my derivative, and then remember what the derivative of a to the n is, or a to the x, or whatever. It's a to the n times the natural log of a. So this is going to be 2 to the n times the natural log of 2. And so now when I put infinity in, I can see that I get 1 divided by infinity, which is 0. And so therefore it converges. There is a problem with this particular one, though. You could not start at 1, which is, this is not a good sequence. Let's say n equals 2 to infinity or something there, just to make me feel better, because you're going to have a division by 0 if you put a 1 in. Okay, so part B. Limit as n goes to infinity of 3n squared minus n plus 2 over 2n squared minus 1. So if I put infinity in, I'm going to get infinity divided by infinity. I can use L'Hopital's, and I forgot to write by L'Hopital's, sorry. This is going to be 6n minus 1 over 4n. And if I put infinity in, over infinity in, I get infinity divided by infinity again. Limit as n goes to infinity, 6 over 4. So this is 3/2. And so, therefore, it converges. Okay? And that's your first little bit of stuff with convergence. Now we're going to talk about bounded monotonic sequences. Lastly, we want to consider those sequences where it may not be possible to determine the limit, but we need to know whether the sequence converges. So we're not going to really worry about, the actual limit. We're going to worry about, does it converge or does it diverge? Okay? So if a sequence A sub n is bounded and monotonic, then it converges. And what does monotonic mean? Well, a sequence is said to be monotonic if its terms are non-decreasing or non-increasing. Okay? So, basically, not monotonic would be like jumping around like in C down here. That is not going to be monotonic, okay? This one is just going down, 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 down. That's monotonic. Each term is less than the previous. This one, each y term is greater than the previous. This one, each y term is greater than the previous. Okay, so... and they've got non-decreasing, non-increasing. Basically, they're using those y values as, if this one is less than the next one is less than the next one, so that would be non-decreasing. This one is greater than this one, and that one's greater than that one, and that one's greater than that one. So non-increasing is like decreasing, and non-decreasing is like increasing. There is a mistake right here. This or should have been and. So please change that in your notes. A sequence is bounded above by a real number m if m is greater than every term in the sequence. A sequence is bounded below by a real number n if n is less than every term in the sequence. So a sequence is said to be bounded if it is bounded above and below. So for part A, you can see that it's gradually going to some number, okay? It looks like 0, but so it is bounded below. It looks to be bounded below. It looks to be monotonic. And it looks to converge. Because it looks like it's looking like it's going to 0, but we're not worried about really what it's converging to. This one looks to be bounded above. It looks to be monotonic. And it looks to converge. And if I had to say what it was going to converge to, 1, 2, 3, 4, 5, probably 6. And that one's probably 0. see it's actually bounded because it's bounded above and below, right? It looks like it's bounded by 1 and -1. So it is bounded. It's not monotonic. And it diverges. I'm just going to say above by y equals 1, below by y equals -1 for the bounded part. But since it keeps like going up, down, up, down, up, down, that's divergence. This one looks like it's going to infinity. It does kind of look like it's bounded below, though. Because it looks like it's kind of, you know, leveling off here somewhere. It looks monotonic. But as n goes to infinity, it is not bounded. So therefore, diverges. And, you know, if you were thinking about what kind of sequences these are, you would say, well, this one is an increasing sequence. This one is actually an increasing sequence also. But do you see the difference between these two? This one is not bounded, right? This one goes to infinity. This one levels off to something, but it's always increasing still. This one is a decreasing sequence. And this one is oscillating.